Hello everyone, welcome back. In this video, we're going to talk about the information that we can extract from derivatives on the shapes of graphs. Now recall from the previous chapter, f prime of x represents the instantaneous rate of change of f of x at a given point. In particular, it will tell us the direction in which the curve will travel at that particular point. Now, the sign of the derivative will tell us when the function f is increasing or decreasing, and this is called the increasing-decreasing test. So if the derivative is positive on an interval, then this tells us that the function will be increasing on that interval. And if the derivative is negative on an interval, then this will tell us that f will be decreasing on that interval. Now this can be used in conjunction with what we learned in the previous section to determine if f of x has any local maximum or local minimums. So recall that the conditions for a function to achieve either a local max or local min was either that the derivative was equal to 0, so it has 0 slope, or if the derivative was undefined. So this could be at sharp corners, for example. So in other words, the function will have a local maximum or local minimum if that point is a critical number. And we can determine whether it's a local max, a local min, or neither by examining the behavior of the derivative near this critical number. And this is what is known as the first derivative test. So the first derivative test says that suppose that c is a critical number of a continuous function f. So either the derivative is equal to 0 at c, or the derivative does not exist at c. Then if f prime changes from positive to negative at c, then f has a local maximum at c. So in the example on the left, we have that 0 is a critical number of the function because it has 0 slope at this particular point. And from negative infinity to 0, the first derivative is positive since the function is increasing on this interval. And from 0 to infinity, we see that the derivative is negative, so the function is decreasing on this interval. And since the derivative changes from positive to negative at this critical number, then this tells us that the function has a local maximum at 0. Similarly, if f prime changes from negative to positive at c, then f will have a local minimum. So in the middle example, we see that the derivative is negative from negative infinity to 0, and then it's positive from 0 to infinity. And again, 0 is a critical number, so the derivative changes from negative to positive on this interval, and so, or at this point, and so we have a local minimum at 0. Now, if f prime does not change sign at c, then f does not have a local minimum or local maximum. So in this example here, we have a critical number at 0, since it has 0 slope at this particular point. But f prime is both positive from negative infinity to 0 and from 0 to infinity. So the derivative does not change sign around this critical number, so it's neither a local max nor a local min. So another feature that we can use to describe the graphs of functions is called the concavity of f. And so we make the following definitions. If the graph of f lies above all of its tangents on an interval I, then it is called concave up on I. And if the graph of f lies below all of its tangents on I, then it is called concave down on I. So in the example on the left, we have the parabola x squared over 2 minus 4, and this graph is concave up on all real numbers. And so what this means is that if we were to draw all of the tangent lines to this curve for every real number, then what we notice is that the function will sit above all of its tangent lines. And so the graph of x squared minus 2 minus 4 is concave up on all real numbers. In the example on the right, we have the parabola 4 minus x squared over 2. Now this function will be concave down for all real numbers. So what this means is that if we were to draw all of its tangent lines at every point on this interval, then we notice that the function is below all of the tangent lines. And so it is concave down on all real numbers. And how I like to think about concave up and concave down is with respect to its curvature. So we see that the function is curving upwards on this interval, so it is concave up. And if it's concave down, then we notice that the function is curving downwards on this interval. So how can we determine the concavity of the function? Well, just like the first derivative will tell us where the function is increasing or decreasing, the second derivative will tell us when the function is concave up or concave down. And so what we look at is called the concavity test. If the second derivative is positive on an interval, then the graph of the function is concave up. And if the second derivative is negative on the interval, then this tells us that the function will be concave down. Now another definition is the following. A point P on the curve y equals f of x is called an inflection point if the function is continuous at that point and the curve changes from concave up to concave down or from concave down to concave up. So in the example here, what we see is that the function is concave down from negative infinity to 0. So we see that the function is curving downwards on this interval. So the second derivative is negative. And the function is concave up from 0 to infinity. So the second derivative will be positive from 0 to infinity. And since the function is continuous at this point, and it changes from concave down to concave up, then this is called an inflection point. So an inflection point occurs if the concavity changes at this point. Now the second derivative can also tell us the location of local max and local min. And so the following test will be an alternative to the first derivative test. So the second derivative test says that suppose the second derivative is continuous near the point C, and if f prime of C is 0, so the first derivative is equal to 0 at C, and if the second derivative is positive at C, then f will have a local minimum at C. And so what we observe is that the second derivative is 0 at a particular point. So it has a horizontal tangent at C, and the second derivative is positive at this point, meaning that it is concave up. And so this information tells us that C is a local minimum. Now the second part says that if we have a horizontal tangent at C, and the second derivative is negative, meaning that it is concave down at C, then this information tells us that C is a local maximum. And so this is an alternative to the first derivative test. So let's have a look at some examples of finding these intervals, the location of local max and min, as well as inflection points. So in the first example, we have f of x is 2x cubed plus 3x squared minus 36x. So let's first find the intervals of increasing and decreasing. So here we'll use the increasing decreasing test. So what we need to test is the sign of the first derivative. So we'll first calculate f prime of x. Using the power rule, this is 6x squared plus 6x minus 36. And we can simplify this to 6 times x squared plus x minus 6. And this can be factored as x minus 2 times x plus 3. So we'll first locate the critical numbers. So we'll set f prime of x equal to 0 and then solve for x. So the critical numbers occur when 6 times x minus 2 times x plus 3 is equal to 0. Solving for x, we get positive 2 and negative 3. So these are our critical numbers. So now we'll use a number line to test the sign of the first derivative. So here we're using the first derivative test. So we will plot the critical numbers on the number line. So what we have are negative 3 and positive 2. So now what we want to do is test the sign of f prime of x within each of these intervals. So between negative infinity and negative 3, between negative 3 and positive 2, and between positive 2 and infinity. So let's choose a number between negative infinity and negative 3. For example, we can choose negative 4. And we want to evaluate the first derivative and see what the sign is. So using the factored form of f prime of x, we have 6 times negative 4 minus 2 times negative 4 plus 3. And this gives us 6 times negative 6 times negative 1, which is positive 36. Now we're not really concerned about the value of the derivative at this point. All that we care about is whether it's positive or negative. So we know that it's a positive number, so f prime is going to be positive on this interval. So this tells us that the function will be increasing on the interval from negative infinity to negative 3. Next, let's test a number between negative 3 and positive 2. So for example, we can choose 0. So we substitute 0 into the first derivative. We have 6 times 0 minus 2 times 0 plus 3, which gives us 6 times negative 2 times positive 3, which is negative 36. And again, we're not really concerned with the value. All that we care about if it's positive or negative. So we know that the derivative will be negative on this interval, meaning that f will be decreasing from negative 3 to positive 2. And lastly, let's test a number between 2 to infinity. For example, we can choose 3, and we get 6 times 3 minus 2 times 3 plus 3. So we get 6 times 1 times 6, which is positive 36. So we know that the derivative will be positive on this interval, meaning that f will be increasing from 2 to infinity. And so this tells us that f is increasing on the interval from negative infinity to negative 3 union 2 to infinity. And then f will be decreasing on the interval from negative 3 to positive 2. So now in part B, let's find the local maximum and minimum values of f. So here we'll use our first derivative test to determine the local max and local min. So using our number line, we know that the derivative changes from positive to negative at negative 3, and negative 3 is a critical number. And since it changes from positive to negative, we know that the function will have a local maximum where x is negative 3. And since the derivative changes from negative to positive at the critical number 2, then we know that we have a local minimum where x is negative 2. So from the first derivative test, we know that f prime changes from positive to negative at negative 3. So this tells us that negative 3 is a local maximum. And if f prime changes from negative to positive at positive 2, and so that will tell us that positive 2 will be a local minimum. So now let's look for the values of the function at these local max and local min. So we need to evaluate the function at these critical numbers. So f of negative 3 is 2 times negative 3 cubed plus 3 times negative 3 squared minus 36 times negative 3. This will give us 2 times negative 27 plus 3 times 9 plus 108. So that's negative 57 plus 27 plus 108. And this is a 81. And f of 2 is 2 times 2 cubed plus 3 times 2 squared minus 36 times 2. So this will be 16 plus 12 minus 72, which is negative 44. And so f has a local maximum value of 81 and a local minimum value of negative 44. Now in part C, we'll locate the intervals of concavity and any inflection points. So to find the intervals of concavity and inflection points, we need to look at the second derivative. So our first derivative was 6x squared plus 6x minus 36. So the second derivative, using power rule, is going to be 12x plus 6. And just like in part B, we will look for when the second derivative is equal to 0, and then we can use the number line to test the sign of the second derivative. So if we set the second derivative equal to 0, we get 12x plus 6 equals 0. So 12x is negative 6. So x is negative 6 over 12, or negative 1/2. So now let's plot a number line for testing the sign of the second derivative. So we plot the points when the second derivative is equal to 0, and we found that happens when x is negative 1/2. And then we're going to test the sign of the second derivative within each of these intervals. So between negative infinity and negative 1/2, and from negative 1/2 to infinity. So let's choose a number between negative infinity and negative 1/2. For example, we can choose negative 1. And so we want to test the second derivative at negative 1. So we have we have 12 times negative 1 plus 6. That's negative 12 plus 6, which is negative 6. So we have a negative number on this interval. So that means that f double prime will be negative between negative infinity and negative 1/2. And since the second derivative is negative on this interval, this tells us that the function is going to be concave down. Now let's test a number between negative 1/2 and infinity, for example 0. And we have 12 times 0 plus 6, which is positive 6. So the second derivative will be positive between negative 1/2 and infinity, meaning that the function will be concave up on this interval. So this tells us that f is concave up on the interval from negative 1/2 to positive infinity, and f is concave down on the interval from negative infinity to negative 1/2. Now, are there any inflection points on this curve? Well, we know that the function changes concavity at negative 1/2. It changes from concave down to concave up. So negative 1/2 is going to be an inflection point. Oops. So now let's determine the coordinate of this inflection point. So let's evaluate the function at negative 1/2. So we get 2 times negative 1/2 cubed plus 3 times negative 1/2 squared minus 36 times negative 1/2 So that is 2 times negative 1 over 8 plus 3 times 1 over 4 plus 18. So that is negative 1/4 plus 3/4 plus 18. So that is 2/4 plus 18, which is 1/2 plus 18. So make a common denominator of 2. We have 1 plus 36 over 2. So that is 72 over 2. And so the point negative 1/2 comma 37 over 2 is an inflection point. So here's the graph of the function that we analyzed. So we go back to our intervals of increasing and decreasing. We saw that the function was increasing from negative infinity to negative 3, and then from positive 2 to infinity, and it's decreasing from negative 3 to positive 2. We determined that the function had a local maximum at negative 3, and its value is 81, and it had a local minimum at positive 2 with a value of negative 44. Now the function was concave up from negative 1/2 to positive infinity. So from negative 1/2 to positive infinity, the function is curving upwards on this interval. And then from negative infinity to negative 1/2, we see that the function is concave down. So it curves downwards on this interval. And the point that the function changes concavity is the inflection point, which we saw to be negative 1/2 and 37 over 2. So let's have a look at another example. So suppose our function was x over x squared plus 1. So let's look for the intervals of increasing and decreasing. So we need the first derivative. So using the quotient rule, we have 1 times x squared plus 1 minus x times 2x all over x squared plus 1 squared. So that's x squared plus 1 minus 2x squared all over x squared plus 1 squared. Simplifying, we have 1 minus x squared all over x squared plus 1 squared. So we can also factor the difference of squares as 1 minus x times 1 plus x. So that is our first derivative. So now we'll look for the critical numbers. So we set the first derivative equal to 0 and then solve for x. So the first derivative is 0 when the numerator is equal to 0. And so this happens when x is positive 1 or negative 1. Now we'll also look for when the derivative is undefined. And this happens if the denominator is equal to 0. So when x squared plus 1 squared is equal to 0. And if you try to solve for x, we'll find that there are no real solutions. And so the derivative is never undefined. So now we'll look at the intervals of increasing and decreasing. So on the number line, we will plot the critical numbers. So they were negative 1 and positive 1. And now we will test within each of these intervals for the sign of the first derivative. So again, we are not concerned about what the value of the first derivative is. All that we care about is the sign. So here we'll just use a bit of a shortcut to determine the sign of the derivative. So we know that the derivative is 1 minus x times 1 plus x all over x squared plus 1 squared. And so now if we choose a number between negative infinity and negative 1, for example, negative 2, then if x is negative 2, then 1 minus x is going to be a positive number. So what we have is a positive number multiplied by 1 plus x, and since x is negative 2, we'll have a negative number. So we have a positive number multiplied by a negative number. And if you look in the denominator, we have x squared plus 1 squared, which will always be positive. And so we end up with a positive times a negative divided by a positive number. This means that the derivative will be negative. And so f prime is going to be negative between negative infinity and negative 1, which means that the function will be decreasing. So now let's choose a number between negative 1 and positive 1. For example, we can choose 0. And if x is equal to 0, then we have a positive number times a positive number divided by a positive number. And this will give us a positive number between negative infinity and negative 1. And lastly, if we choose a number greater than 1, for example, 2, and if we substitute 2 into the first derivative, we have 1 minus 2, which is a negative number, times 1 plus 2, which is a positive number, divided by a positive number. And this will end up being a negative number. And so the function will be decreasing from positive 1 to negative infinity. So the function will be increasing between negative 1 and positive 1, and f will be decreasing on the interval from negative infinity to negative 1, union 1 to infinity. Now in the next part, let's look for the local max and local minimum values of the function. From our number line, we know that f prime changes from negative to positive at negative 1. So there is a local minimum when x is negative 1. And since the derivative changes from positive to negative at positive 1, then we have a local maximum when x is positive 1. So let's determine the values at these critical numbers. So f of negative 1 is negative 1 over negative 1 squared plus 1. That is negative 1 over 1 plus 1, or negative 1/2. And f evaluated at positive 1 is 1 over 1 squared plus 1, which is 1 over 1 plus 1, or positive 1/2. And so the function has a local minimum at negative 1 and negative 1/2, and f will have a local maximum at positive 1 and positive 1/2. Now for the third part, the intervals of concavity and inflection points, you will need the second derivative. So our first derivative was 1 minus x squared all over x squared plus 1 squared. So we'll use another quotient rule to find the second derivative. So we have negative 2x times x squared plus 1 squared minus 1 minus x squared times 2 x squared plus 1 times 2x. And that's all over the denominator squared, so x squared plus 1 squared squared. So now let's simplify. Let's take out a common factor in the numerator. We see a common factor of 2x and x squared plus 1. So let's factor that from both terms. So that is 2x, x squared plus 1. And we are left with a negative x squared plus 1 from the first term, and minus 1 minus x squared times 2 from the second term. And that's all over x squared plus 1 squared to the power of 2, which can be simplified to x squared plus 1 to the power of 4. So now let's simplify. We can cancel out one of the factors of x squared plus 1, and we are left with 2x times negative x squared minus 1 by distributing the negative, and negative 2 plus 2x squared by distributing the negative 2 to the second term. And that's all over x squared plus 1 to the power of 3. And simplifying, we have 2x times x squared minus 3 all over x squared plus 1 cubed. So there is our second derivative. We will set the second derivative equal to 0 and solve for x. So the second derivative is 0 when 2x times x squared minus 3 equals 0. So that's x equals 0, or when x squared minus 3 equals 0. Solving this equation, we get x is plus or minus the square root of 3. And if you check for when the derivative is undefined, we see that there are no real solutions for when the denominator is equal to 0. So the second derivative is never undefined. So now let's plot on the number line the zeros of the second derivative, which we found to be negative root 3, 0, and positive root 3. So now let us test the sign of the second derivative within each of these intervals. So we know that the second derivative was 2x times x squared minus 3 all over x squared plus 1 to the power of 3. So now let's choose a number between negative infinity and negative root 3, for example, negative 2. And we substitute negative 2 into the second derivative. We get a negative number. Now negative 2 squared is 4 minus 3, which will be a positive number, and the denominator will always be positive. So multiplying this out, we get a negative number. So the second derivative will be negative on this interval, so it will be concave down. Now let's choose a number between negative root 3 and 0. We have negative 1, for example. So if x is negative 1, we have a negative number times negative 1 squared is positive 1 minus 3, which will be negative, all over a positive number, and this will be a positive number. So the second derivative is positive on this interval, so it will be concave up. Now let's test a number between 0 and root 3. For example, positive 1. We get a positive number times a negative number over a positive number. So this will be a negative number, so it will be concave down on this interval. And lastly, let's choose a number greater than root 3. For example, positive 2. Then we get a positive number times a positive number over a positive number. So f will be concave up on this interval. So f will be concave up on the interval from negative root 3 to 0 union root 3 to infinity, and then f will be concave down on the interval from negative infinity to negative root 3 union 0 to root 3. So now let's look for inflection points. We see that the second derivative changes concavity at 3 different points. When x is negative root 3, when x is 0, and when x is root 3. So we have 3 inflection points, since the second derivative changes concavity at each of these points. So we need to find the coordinates of these inflection points. So f of negative root 3 is negative root 3 over negative root 3 squared plus 1, which is negative root 3 over 3 plus 1. So that's negative root 3 over 4. Next, we'll evaluate 0. So that's 0 over 0 squared plus 1. That's 0 over 1, which is 0. And lastly, at positive root 3, we get root 3 over root 3 squared plus 1, which is root 3 over 3 plus 1, which is root 3 over 4. So the inflection points for this function are at negative root 3, comma negative root 3 over 4. We have 0, 0, and we have root 3 and positive root 3 over 4. So here's the graph of the function. So what we observed is that the function is decreasing from negative infinity to negative 1. It is then increasing from negative 1 to positive 1, and then is decreasing from negative 1 to infinity. We found the local minimum at negative 1 and negative 1/2, and a local maximum at 1 and positive 1/2. Next, we found that the function was concave down from negative infinity to negative root 3. So here is negative root 3. So the function is curving downwards on this interval. And then from negative root 3 to 0, it is concave up. So that means that this coordinate is an inflection point. And then from 0 to root 3, the function is concave down. So the origin is another inflection point. It goes from concave up to concave down. And then from root 3 to infinity, it is concave up. So again, another inflection point is at root 3, since it goes from concave down to concave up.